This video is for topic 5.3, concentration changes over time. The objective for this topic is to identify the rate law expression of a chemical reaction using data that show how the concentrations of a reaction species change over time. We use what are called integrated rate laws, and these are equations that we use to evaluate or create a graph or to calculate the order with respect to a certain reactant. And so the two things that we look at are the concentration at a specific time and then the amount of time needed for a reactant to actually react. We end up with three different common types of orders. We end up with zero order, which the equation for zero order is that our initial concentration minus the concentration of our reactant at a certain time equals the constant times T, or time. A first order reaction is the natural log of the concentration at a certain time divided by the initial concentration equals the negative rate constant times time. And then a second order reaction is the inverse of our concentrations. So 1 divided by a reactant, the concentration of a reactant at a certain time, minus 1 divided by the reactant, the initial concentration of the reactant is equal to the rate constant times time. We're going to be a little bit more familiar with these if we manipulate them to look like the equation of a line. So we're going to talk about zero order first. A zero order reaction is going to produce a graph of concentration versus time that has a negative slope. And then your slope is your rate constant. And so what we see is the change in concentration is consistent for the entire reaction. For a first order reaction, the change in concentration is going to be greater at the beginning of the reaction, and then it's going to slow down as time progresses. We get a linear graph when we do the natural log of the concentration versus time. So a natural log graph is going to give you a negative K slope. So your rate constant is the negative slope of your line. A second order reaction is similar to a first order, except a little bit more dramatic. So the change in concentration is going to be even greater initially in the reaction, and then it's going to slow down as time progresses. To get a straight line graph of this type of reaction, you would graph 1 over the concentration, or the inverse concentration, versus time. You get a positive slope, and that slope is your rate constant. So we can use our graph of a reaction over time, so we can do this experimentally and measure the concentration of our reactants over time as the reaction progresses. And what that data does then shows us whether it is first order or second order with respect to that particular reactant. If concentration versus time gives us a straight negative slope line, it's zero order. If natural log of concentration versus time gives us a negative slope straight line, it's first order. And if the inverse concentration versus time gives us a positive slope straight line, then the reaction is second order. A common use of kinetics or this rate changing is half-life. We often talk about half-life with radioactivity. Half-life is the time required for the concentration of a reactant to decrease to 1/2 of its initial value. And half-life is a first order reaction. So that means over a unit of time, the concentration is going to decrease by half, and then over the same unit of time, it's going to decrease by half again, and then the same unit of time is going to decrease by half again. So that's a common application of a first order reaction, is the half-life of a radioactive species.
So this question is looking at the reaction 2A producing B and C, and we have two sets of data that's collected. We have a graph for the inverse of concentration of A versus time, and we have a graph for the natural log of A versus natural log of the concentration of A versus time. We know that from our graphs, if it's just A, concentration of A versus time, that's a negative slope, that's a zero order. we know that the natural log of the concentration of A versus time with a straight line negative slope is a first order, and the inverse of the concentration of A versus time, straight line positive slope, is second order. So it's our natural log of A versus time with a negative slope of a straight line that matches our data. So we have that here. So that graph tells us that this is a first order reaction. And our rate law would be rate equals K times the concentration of A raised to the 1. Part B asks to describe how we would determine the value for the rate constant. With this data, we know that our rate constant is equal to our negative slope. So we would need to know the slope of the line, and then the negative of that slope gives us our rate constant, or K.